Anybody still logging in? Navigating to my directory. Can I continue? Alright, continue I will. So yeah, go ahead and check analog or mixed AD, so make sure you can run sims. Name it whatever you want. Make sure you put it somewhere you can find it, so drop down here, find your P drive, probably, or you can put it on your flash drive or whatever. And I'm just going to put it here. Then you hit OK. This doesn't really matter. I like to create a blank project and then hit OK. Did I lose anybody yet? Alright, good. Alright, so basically we have a little circuit here on the page. What I like to do first, come over to the right here. There's a little, looks like a little chip or a bug with a plus on it. That's where you place parts. And then you come down to this rectangle with the shiny thing on it. That's how you add libraries. You need to add all the PSpice libraries to make sure you have the parts to simulate. Make sure you're in the PSpice folder up here. If you're not, get to it by doing this. Make sure you're in PSpice and add all the libraries. Just highlight them all. Anybody not find their libraries? Okay, open them up. Here they are. So these are just a whole bunch of parts that you can work with now. The only thing we need out of there is our transistors, but I like to add them all anyway. Okay, so when your first step is to draw your circuit in PSpice over here. So what I would start with is just add all the parts you know you need and then connect them together later. So these transistors in the lab, we always use the Q2N. So you come over here, part right here, and you can type in what you want to search for it. So the Q2N3904, that's the BJT that we usually use. So you look that up, it'll come up here, it'll say /eval. You can see a little picture of it down here. To place it, double click it, and then you can just click. So we're going to have two of them, so you can just put them there by clicking twice. Once you have two, you just hit escape and you'll stop placing them. So now we got two of these guys floating around. And then I'm going to go ahead and close this window because I have a very small screen to work with. Okay, next we're going to want all our passive components. So we need 1, 2, 3, 4, 5, 6, 7, 8 resistors. So come up here to place in the little file edit bar. Place, PSpice component, passives, R for resistor. Grab those. I'm just going to throw down 8 of them so I have them for later. And then hit escape to stop placing them once you've got all you need. Same thing for your capacitors. Looks like this circuit needs 4 of them. So we'll go to place, PSpice component, passives, C for capacitor, and we'll grab 4 of those. And hit escape to stop placing. And okay, now we want to add voltage sources, so we'll need 2 kinds of voltage sources, DC and AC. So for the AC source, again, you go to place. This is where most of your stuff's going to be. Place, PSpice component, source, voltage sources, not AC. AC is nice, but what we like to use is sine because it lets you do more things. It lets you run a transient simulation, like over time, and also a frequency sweep, like a Bode Plot. So it's handy for that. So go ahead and click on sine under voltage sources. You've got this little guy. Just leave them there. And then for your DC sources, go the same thing, place, PSpice component, source, voltage, and DC. And we'll want 2 of those. We'll just leave them floating over there. Okay, now we can start building it. So we'll just go left to right, we'll start with this voltage source, so that'll be the base of everything. You got them there. To place a ground, just press G on the keyboard. It'll bring up a little ground menu. You want the 0 cap sim. The picture shows up. It's a little ground guy with a 0 in the bottom right. That's the one you want. Hit OK, and you can just boop, stick it right there. If there's a red dot, that means it's going to make a connection. And then from there, when you want to place wires, you press W on the keyboard, and it'll create this little cursor, so you have a little crosshair, and you can just click on connections and start drawing wires. And you can draw them wherever you want, hit escape to stop drawing, and then you can highlight and hit delete to get rid of them if you want to get rid of them. Anybody lost? Alright, so we're going to start building left to right. We're going to start with this first resistor, connect it with the wire. And this resistor is going to be this is what you call RG. This is just a property of the voltage source. So like if you were building this circuit physically, you wouldn't put a 50 ohm resistor there, but we will. So to edit the value of the resistor, you just look at the value right there. So they're all 1K by default. Just double click on that, and then you can type in your own value. So for this one, just 50. Okay. Now it's a 50 ohm resistor, and PSpice knows it's a 50 ohm resistor. For this voltage source, we're going to start this AC value. So this is when you run an AC sweep simulation. This is the voltage value it'll use. So you can just use 1 volt. That's the easiest way. This V off, just always set that to 0. And then in the middle, these two are for when you run a transient simulation. So this is what the voltage source will do when you just simulate the whole circuit. So V amplitude, it's usually going to be something smaller because the real circuit is limited by your DC sources. So just make it like 0.1 and I don't know, 100K or something for now. We'll fix it later. But that's a good place to start. And we'll continue building the circuit. When you have a resistor that you want oriented vertically instead of horizontally, or any other part, select it so it's pink, and then hit R to rotate it. So just hit R, now it's that way, and you can drag it over here. So I'm just going to go ahead and slowly build this circuit. And you can just kind of manipulate things however you want. You can highlight stuff, drag it around so that it's easier to read or whatever. So I'm going to slowly build this circuit. Let me know if I get too far ahead or if anybody gets lost. But you just follow along. So that piece of paper you have has the regular drawn circuit and the PSpice made, so you can just follow along. With these voltage sources, something you can do, so like at the bottom there we have a -5 volt source. An easy way to do that is take the source, flip it upside down. It's kind of hard to see the plus and minus. If you hit Control and scroll up, you can zoom in, or you can just see that the longer line is the positive. I forgot about that, I had to relearn it, so I'll tell you. So you can just flip the voltage source upside down so the positive is down here, and then call it 5 volts DC, and bam, you have a -5 voltage source. You can drag this text out of the way, put another ground in, and it's good to go.
Tim, did you already cover the R's rotate?
Yes.
Okay, good. I missed it.
Anybody struggling? You guys know what you're doing. So in PSpice you can use the suffixes for units. So like if you want a 100K resistor, you put in the letter K, and it knows it's a 100K resistor. You can also, if you don't want to like lay all your parts out beforehand, you can just have a resistor and then you can use Control-C, Control-V and just copy and paste it over and over again. You can do a lot of things. A lot of freedom. Oh, I forgot a cap over here. Alright, so I forgot this capacitor, so what I'll do, slide all this crap over, delete this wire, and just put the capacitor in. Easy. These are going to be 0.1 microfarad. So for micro, obviously you can't type a mu, so you just type a U, and that's your micro units. So that's a 0.1 microfarad capacitor. So with this voltage source on top, it's actually going to be upside down as well, because you want, so these are going to appear the same orientation, but you want the positive side of it in contact with this rail, right? So that's a positive 5 rail. Doop. And I don't actually know if you need to leave this VDC in here. It's always in there, so I usually just replace this number. Do you know, Dr. A?
I don't think it cares about it.
Yeah, probably not. But it looks nice, so. And you can put your grounds upside down. If you copy a part and then paste it, you can't rotate it until you've placed it. And then you can rotate it. But if you just copy it and paste it and then try to rotate it, it won't do it. So you gotta place it first. What else was this? Try to expand some of this so it's easier to see. Oh boy. Oh boy. Oh no. Don't do that. Alright. Who's still making their schematic? Is everybody still making it? Anybody? Alright. Sounds good. Thanks, guys. Andy, do you want to like walk around and see if anyone needs help and stuff?
Yeah.
Alright, so we've done all that. The next step is to check our DC biasing by doing a bias point simulation. So that's always the first simulation we run to make sure the thing's not broken. So a bias point simulation is just going to look at the stuff from the DC sources and not this AC source. So the caps will act like open circuits, all that nonsense. So we'll just look at DC stuff. So to do that, you go up to PSpice again, or I guess this is the first time, but you go up to PSpice on this bar up here, and you create a new simulation profile. You can also just click on this, the shiny sinusoid over here, make a new simulation profile. Either way, open it up, call it something. Don't call it anything too dumb, because it will show up when you print out your simulation results. And then it'll pop up a little window where you can edit your simulation stuff. So you want to go to analysis type, there's a little drop down, and for now we're doing bias point. So you just click on it, don't worry about any of this other stuff. If you really want to, you can hit apply, and then you can hit OK. So now the simulation is set up to do a bias point. Is anybody struggling with the bias point thing? Alright, I'll wait a sec. Okay. So once you have created your simulation profile, you can just come hit the play button here to run your simulation. Hit that, and it'll pop up with a new window. We don't need to worry about this for now, because we're just looking at this. So you can see a bunch of little red tabs popped up with voltages on them. If those don't pop up, you can turn them on here with this V, and you can also turn on your currents. So it looks really ugly with the voltages and currents on there, but you can drag these little boxes around so that things are a little more legible. They connect with little lines. So the bright red is the current, and then the purpley red is voltages, which, I mean, okay, they have units on them, so you can tell. So you can see we have here like a 1.18 milliamp collector current, and then an 8.6 microamp base current. So that looks pretty good. That's about what should be happening. If you notice, sometimes you'll see a negative current, because the way this thing works is that, here I'll zoom in. The currents only show up at the the connectors of components, and they measure the current that's going into that connector. So these ones are positive because the base current's coming in, collector current's coming in, but here this one's negative because there's positive current coming out of the emitter. So that one's negative, but there's a positive one right here. So I like to get rid of the negative ones because they're just clutter. You can just click on them and hit the delete key and they'll go away. Because this is going to be the same current. So yeah, you can drag them around. When you save your file and close it and open it back up again, it'll remember where you dragged these to. So once you clean it up, it'll stay cleaned up. One thing, if you notice, if we were to solve this problem by hand, and we assumed beta was 100 like we did in class, you would not get these values, because these simulations, these guys have properties based on the real component in real life. So you're better off looking up the data sheet and trying to find those things. So these betas are more like 140 or something like that.
165.
Okay, 165. So yeah, when you're doing your calculations for that final project, make sure that you're using values that line up with the actual component values. So there you go. That's a bias point simulation. That's what you get out of it. This gives you all your DC stuff, so you can check what you hand calculated for your collector current, base current, collector voltage, stuff like that. The next kind of simulation we want to run is an AC sweep. So this is where you get a Bode Plot type printout. So we're going to look at the circuit's response to various frequencies. To do that, you can either hit this little sinusoid here with the pencil, or you can go up to PSpice and edit your simulation profile. You can also make a new one, but it doesn't really matter. I just always edit the same one. I just remake them every time you run the program. So now analysis type is going to be AC sweep / noise. And here you actually do have to mess with some settings. So your start frequency is going to be the lowest frequency that the simulation looks at. So for this one, 100 is a pretty good place to start, and you can just play around with it while you're doing it. And then 100 megahertz is where I want to stop. So something to keep in mind, a capital M in PSpice is still milli. Whether it's capital or lowercase, it's still milli. So you got to type out meg. It can be lowercase or uppercase,
Super important.
but you do need it to say MEG if you want mega. Otherwise, it's going to run from 100 hertz to 100 millihertz, and you're going to get nothing good. So MEG is for mega, whenever you're doing mega. Points per decade, this is just how many data points you're going to grab. So 100 is usually good. Any questions? Cool. This should be on by default, but make sure you're looking at a logarithmic scale by decade, because that's how we draw our Bode plots. You can also do by octave, but that's weird. Don't do that. All these are fine. Everything else is fine. And yeah, you can just hit OK. So now the simulation type is an AC sweep instead of a bias point. These values will stay here for you, which is cool. So you can just leave them here, and I think they'll actually change when you run the simulation, I'm not sure. But these guys will stay here for you, so you don't have to worry about those. To run the AC sweep now, you just go up and hit the play button again. Oh wait, no. Before you do that, you're not going to get much out. So a handy thing in PSpice is net aliases. You can find those by going to place net alias, or you can just hit the letter N on the keyboard, and it'll bring up a text window. This is how you can label a node. At PSpice, by default, all the nodes have names, but they're just a bunch of nonsense letters and numbers. So I like to make an out and put it on the output here, right? So this is going to be our V out. So you just touch it to the wire where you want your output voltage. So this is now the out node. You hit escape and you'll stop placing outs. So now that stays there. Hit N again, make one for in, and we'll put that one, we'll put it here. So our input voltage is not going to be VG, right? Because VG includes the voltage generator, the voltage source thingy includes this resistor. That's part of that. So our actual input voltage is going to be over here. So we got an in, we got an out. You can also, if you're just looking for like quick measurements, you can use a voltage marker here. You can use a little probe, and you have this little probe. You can hit R to rotate it, and you can just poke it in to where you want to measure voltage, and it'll show up on your plot. I'm not going to do that because I'm going to do a different thing, but that is a handy way to do it. Does anybody not have their net aliases made? Alright. So go up and hit play again. This window will pop up, and you'll actually look at it this time. So this, there's nothing on it yet. If you want to actually look at some stuff, you can right click on the window and hit add trace. So that'll add like a scope trace. And then this window really sucks and is hard to use if you're not careful. Basically what you want to do is uncheck most of this stuff. We're just looking for voltages, right? So you can see our voltage here. You can see it's handy that we named it out, because otherwise it would just be one of these nonsense things. So don't click on it yet. What you want to click on is dB over here, so that you can, dB just stands for decibels. So V out is naturally just going to be in volts. You want it in decibels, you click dB, and when you click on it, it automatically fills this little text box here, and it puts your cursor inside the parentheses. So you hit dB, and it says, okay, you want what in decibels? And then you click V out, and it goes inside the parentheses. And now you have dB of V out. If you clicked things in the wrong order, you're kind of out of luck. You got to highlight it, delete it, because as you click things, here I'll show you, they just show up in the box, and it's a disaster. So make sure that you click in the right order, dB, V out, You can type it in too if you know exactly what you're typing in, but it's easier to just click on stuff. And then when you hit OK, you now have a Bode Plot type thing. This is your frequency response. So on the left side, the y-axis, you have decibels. There's 0 down here. It's attenuating down here. And then on the x-axis, you have frequencies on a logarithmic scale. So next thing you might want to do is find your... I will hold on. Did you go to 100? I did, yeah. If you go to 10, it counts.
Did you simulate it to 100 megahertz?
I did simulate it to 100.
Put 100K for frequency, right? Oh, no, I made this.
Yeah, but it doesn't.
It looks like that isn't connected. Your values are wrong. That should be right. You said 3.
Yeah, yeah. So like all this stuff is wrong.
Oh, okay. Check out your sources. It's not even that much. I mean, you guys have never been in Jack chats and want them as well. That's too much. Yeah, it doesn't have to be as bad as something else. It still kind of does. And this is already yeah, it shows up in the he's barely this is it. Oh, you drew this one. Oh, it's there. That's over. Yeah, that makes more sense. It's frustrating. Oh, that makes sense. Okay.
No wonder, I trouble making it. Like, why is it
I really would prefer to stay busy with closer concepts.
Yeah.
It's a good idea. That VN is a good place to illustrate that. You got 2 wires crossing.
Yeah. Alright, so a couple of people had a problem with this junction here where you had wires crossing each other instead of actually intersecting. So if you look, there will always be a pink dot. If 2 wires are actually intersecting, you should have a pink dot. So like here, 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 there's a pink dot. If there's no pink dot, like say for instance, instead of connecting those wires, you drew a wire straight across, they're not connected. It looks like they're connected, but they're actually not connected. So this would be a different node from this, or I'm sorry, this would be a different node from this. So to fix that, go ahead and just delete one of the wires, redraw it, and make sure that you click when the red dot shows up to connect there, and then continue on and connect to the next spot. Make sure you get the pink dot. Alright, does anybody not have a plot that looks kind of like this? That's Holly probably doesn't. Excellent. Alright, well, I'll keep going. So, let's say you want to find the mid-band gain. You can come up to this little fx here, evaluate measurement. Hold up. Who says this? Alright. Can I keep going?
Yeah.
Alright. So, you can find that here, or you can go to, I don't even remember where else it was. Okay, so yeah, that's here.
Yeah.
And then, I don't know if you can do it any other way. Yeah, so you want this little, it's a little square, says f of x, evaluate measurement. So this is where you can do all sorts of neat stuff. So these are all your functions over here, and then these are all the places you can get data from. So again, we're going to uncheck all these so we just have our voltages. So for the midband gain, you're just going to look for the highest point, right? So you want to find max. These are alphabetical, so just find the word max. So this is going to find your maximum value, and then max of V out. Hit OK, and it'll show up here in the middle of the screen. So max of V out, 100 and... Oh, I have to turn that into decibels too, don't I? Because it gave me 193 volts. Okay, so it spat out 193.5 volts because V out is in volts. If you want that in decibels, which we do, you're going to instead hit... Oh, geez. Okay, now this gets weird. So you're going to hit max. And now I got to find this dB thing. Is it in one of these, Dr. A? Okay, Jesus. So in measurements, you're going to hit max, then come up in this drop-down window to analog operators and functions. Find dB. So now we're looking for the max of the decibel converted value of V out. So you can stack the functions, hit OK, and it'll spit out 45.7 dB is our midband gain. Or, because we put in 1 volt for that AC source back here, this 1 volt, that's what's used during the AC sweep. So you can also say that, 1 volt times, or the max divided by the 1 volt or whatever, you have about 193 volts per volt gain. A little bit. It's close. And then that's our max decibels. You want me to do V out over V in for that? Should I do that right here? Okay. So, to be a little more accurate, you can also do division and stuff. So, if you don't want to go up to this FX, once you have this open, you can click on this little pink bar, evaluate a new measurement. So, if we want to get really fancy, we can look for the max of the decibel value of V out slash, hold on, which parentheses am I inside of? So this is kind of ugly, but you can do V out slash V in to divide. So because our V in is not going to be exactly VG, that's something you can do. That's kind of ugly, but that'll give you your actual gain.
Quick note, when you use those functions and you hit like dB or something, then the first thing that you hit will throw you outside of the parens, so you'll have to back up if you want to do division or something like that. Right? And if you don't want to go through these menus, you can always type in like dB or E or something like that.
Yeah. And it's something you can do if you're just that good. That's probably a good idea, because clicking on these kind of sucks. So you hit OK. So, real close. Our actual gain is 45.9 decibels. So, pretty much the same. Okay, so we also want to look at the phase. So to do that, that's just another measurement you can do. So first, we're going to right-click on this plot, and we're going to add another plot. So now we have 2 plots. And that's real squished, but this is going to be our phase plot. So now if you right click on this empty one, you can add another trace. This one, instead of being decibels, you're going to go down to P for phase. P stands for phase. And not power, because power is just PWR. So P is phase. You want P of V out over V in. So make sure you're inside the correct parentheses. V out slash V in. So now we're going to look for the phase of our thingy. So this plot, it's got the same x-axis, it's just your frequency. On the y-axis, the D stands for degrees. So our phase starts down here at, I don't know, negative 90 degrees or something like that. And it just kind of wiggles around. And you can change the size of that so you can see it a little bit better. Okay. Some other things you can find from your actual V out plot. You can find your cutoff frequencies. So, oops. So make sure you've got this plot selected, or I guess it doesn't really matter. Evaluate measurement again. So for the cutoff frequencies, if you want, say, your lower cutoff, you're going to look for cutoff high pass. The reason for that is, think about if you have a high pass filter, the only cutoff frequency you're going to look for is the lower one, right? So you want the lower one. You look for cutoff high pass 3 dB. There's a couple of them, but it just stops at 3 dB. That's the one you want. Click on that. Put in your V out, and we'll put in our V out over V in. And when you hit OK, cutoff high pass of that, 65.8 kilohertz. That's our lower cutoff frequency for this circuit. You can do the same thing for the upper cutoff. So this time you find cutoff low pass, V out over V in, and it gives you that. And you can expand this so you can see them all at the same time. So our upper cutoff frequency is going to be 5 megahertz. So we have a pretty big bandwidth. Is anybody not good with the frequency measurements? So a couple handy things. We're running out of time, so I'm going to speed up a little bit. This little arrow gives you a cursor that you can drag around. It's right here, so on the same bar as the evaluate measurement. So you can drag this cursor around, and the values of this cursor are going to show up in the bottom right here. So I'm using the red cursor, right? It's red, Y1, and I want to say find a good mid-band frequency. So this is all pretty much mid-band, so you can use any of these. But I'm looking for where my dB V out is about what I got for my max. So 45 point something, I get, let's say, 502K, doesn't really matter, for a frequency. So just, you can write that on the plot, so like when you print it out, if you want that to be on there. To add text to your plot, you can just hit plot up at the top, label, text, and then you can write stuff on your plot. So you could say like FMB, it's not even a thing, equals 502 kilohertz. Okay, and then you can just slap that on somewhere, and it'll show up. Well, I would hope it would show up. Where'd it go? I think it's because everything's real squished. There it is. And it's kind of ugly. It'll look better when you print it out. If you want to print this out, just hit Control P, and you can print it. I like to print it to a PDF first. It just lets you save it as a PDF, or you can just print it right out. So
this is good for
Yeah.
like finding the phase margin, right? Because we can navigate to where we have the zero crossing and then evaluate exactly what the phase shift is at that point.
yeah, turn off these cursors. So
And
yeah,
you can add like arbitrary lines and stuff like that, but you don't have to worry about it.
yeah, these cursors are pretty handy. Okay, so that's the AC sweep. We'll cover the transient then, Dr. A? Kind of like 4 minutes. So when you're done looking at all this stuff, you can just
Let me pause you for a second.
okay. So when you're done looking at all this stuff, you can just close the window, and we're back here where we started. So the last kind of simulation you want to run is a transient simulation. So we just looked and found the midband frequency that we want to use. So you can put that, so for the transient simulation, that's going to use these values of this sine source. So our frequency, we want it to be about 502K, right? So because we want to look at the midband. So you can put that in there. This V amplitude, it's going to be small because it's limited by these guys. We don't know how small yet, so we'll just leave it there. This transient simulation is going to be handy in the project for finding out where what your voltage swing is, where it clips. So we're just going to go up to PSpice, edit our simulation profile, and do a time domain transient. So let's run this one for, I think I want to run it for like 10,000 nanoseconds. You want to be careful in this window. I'm not going to set any maximum step size for now. If you do set a maximum step size, basically it's just setting again how many data points you're going to get. If you make your max step size too small, it's going to get too many data points and you're going to freeze the program and you'll have to close it and try it again later. So I'm not going to set any for now. We'll see how it looks. I'm going to run to about 10,000 nanoseconds and see what that looks like. So I'm going to say OK, and I'm going to run it. Actually, here for this one, I'm going to show you how to use this voltage probe thing. So I'm just going to grab this voltage probe, stick it on the output, and now when we run this, what this probe is connected to is just going to show up right on the screen right away, so we don't have to go dig around for it. So I'm going to hit play, and there it is. So you notice that this is really square and not sinusoidal, right? That's because it's clipping. So if your circuit's clipping like that, that means you're trying to go beyond your voltage swing that you can do. So just go ahead and close that. Mess with your amplitude that you're putting in, and I happen to know that 0.005 volts is a good one for here. I think in the final project, Dr. A gives us an input voltage that we have to have, and then a voltage swing we have to get out of that. So you won't have to mess with it, but for now, I'll change that amplitude, run it again, and then that looks better. It's a little jagged, and that's because of the max step size. So if I wanted that to look even prettier, we could go edit the simulation profile, set the step size to I don't know what I set it to. Let's say 0.1 microseconds. Let's see what that looks like. It looks better. Alright, cool. Now it's a little smoother. So here this is what's happening. So now on the x-axis we actually have time, so you can see like the period of the signal and all that kind of stuff. From here, basically what you want to get out of this is your voltage swing with a given input. So if we put in 0.005 volts, we get a swing of like almost a volt peak. And you can measure this just how we measured the last one with all the same tools. So you can just go to max, uncheck all this crap, V out, and you'll see like 970 millivolts is what you get out. And then if you want to do the math, you can do that. I don't want to do that. So I think I can just do math in here. Let's say V out over V in Ah, no, I can't do it. Crap. That doesn't work? I was hoping it would just spit out. Did I do it wrong?
Spit it out here because you're measurement. But,
Okay.
well, actually, yeah.
Where can I
it
I
should-
type?
was evaluating, that should have worked.
yeah.
Where's my... I don't have a V in.
What is your V in? Is not showing up though.
Yeah.
That's a problem.
Oh, my in's gone. Where'd it go?
Oh,
Oh, it left when I deleted that wire. Oops. Okay. There's in. Do you think it'll just know now? I better run it again. So yeah, you can do some math in that little window. Jesus Christ. Well, maybe not. I don't know. That ought to work.
Okay, select them.
Maybe.
Problem with the probe.
Think so? Anyway, so you don't have, I just don't have a calculator handy, so that's why I'm trying to do it in there. You just do it in your calculator, the input voltage you put in, this V out you got, and you'll see that the gain is what you got for your mid-band gain. That's all I wanted to show you. But yeah, this is most important for seeing your voltage swing, so you can just keep putting in stuff till it clips.
That's because you want, you're doing value measurement, right?
Yeah.
That gives a value, and V out and V in are not values, they
Ooh.
are traces.
Oh, so I'd want max V out over max V in or something like that. Okay, good point. Well, there you go. Is there anything else we need to cover? We're over time. Is that good? Alright, cool. Then I guess we're done. Yeah, I'll sit here if you guys have questions.